All right, we're talking about center of mass by calculus now. So when we were using a non-calculus method, we had our vector center of mass is equal to, a summation from I equals 1 to n of vector r sub I times m sub I all over a sum over I equals 1 to n of m sub I. Well, summations turn into integrals when you take and make things really small. And in this case, we're making the weighting really small. We're making the mass really small. So we're going to be looking at really tiny masses. That means RCM is going to become integral r as a vector times dm over the integral over dm. If the material is uniform, then we can rewrite this in one final form. RCM as a vector is 1 over the total mass, integral of vector r dm. We can also, just as before, split this up into x and y components separately. Works just as fine and just as well. But it does raise the question of what the heck is this dm thing? So let's say we have some 2D object and we'll put it in an xy coordinate system. dm is a small little piece of that. So we'd need to find the mass of a small little piece. Sometimes double integrals are useful, sometimes triple integrals are useful. We're actually going to learn how to do this without appeal to any of those. What we're basically going to do is take convenient shapes. So we're going to imagine chopping things up. So we will be imagining chopping a shape up into simpler shapes, where each of the simple shapes is the same distance along x or y from our origin, and the entire shape, well, simple shapes where the entire shape is that distance from our origin. Then we will use geometry to find the volume of that shape, and the density, D-E-N-S-I-T-Y, to find the mass of that shape. That's going to be our whole trick here. As a simple example of how this might work, imagine if we wanted to find the center of mass of a rectangular solid. Pretty straightforward idea. We'll set up our y and x coordinates, so we put 0, 0 at the lower left corner. And now we'd be thinking about how would we divide this up. Let's say we want to find XCM by calculus. So that's going to be 1 over the mass times the integral of x with dm. We want to think about what is dm going to look like. Well, we want everything to be the exact same distance along x, so we're essentially going to put this in a salami slicer and get a lot of thin vertical slices out of it. And one of those thin vertical slices we will say is our dm. It has, in this case, an area dA. We're splitting it up along the x-axis. That means along the x side it has a width x and it has a height y. So area, or d area, would be y dx, and dm would be equal to the area density times r dA. Now that does raise another point. What do you mean area density? Well, there are 3 types of density we will deal with. Linear density, area density, and volume density. And you've at least heard of volume density before, you're familiar with that, but these other 2 may be unfamiliar. We're going to use the following symbols when we deal with them. Lambda, lowercase lambda from the Greek letter set, for the linear density. Lambda is equal to the mass over the length, or dm over dl. You'll notice I'm using lower cases usually for variable things, for infinitesimals, and I'm using uppercase generally for the constants. Okay, area density, which is sigma. Sigma is the mass over the area, or it could be dm over dA. I probably should change my dA up here to match then. Because lowercase is not a bad idea to make it clear that what we're talking about is an infinitesimal quantity, something that can vary. Okay. That's fine. Let's change tool back. And then volume density, the one you're familiar with. Volume density is the mass over the volume. And you can think about that as dm over dv, where dv in this case is representing a volume, not a velocity, so be careful. All right, in this case, we would be dealing with something that is an area density, so we'd basically have mass over the length times the width equal to dm over dA, and that's where we would get our density from and use over on the other side. Now in this case, y would just be equal to the width if we have this as length and width. All right, this is just a quick example of what we're going to be doing. I am going to try and record example problems of this immediately in the next week. So if you're in a future class, you won't even notice. If you're in my current class, it being fall of 2021, there will eventually be a couple example problems that walk you through the process of doing this from end to end. All right. We're going to stop this one here. The example problems are going to teach you a lot. Make sure you watch those videos when you get a chance. And see you in the next video sets.